This is an introduction to the technique called substitution in integration. It's by far the most important technique there is in integration, and then all the other sophisticated ones that come after this, by and large, will rely on substitution. So this is a rather important subject to do in integration. Okay, so to warm up, let's look at some indefinite integrals that can be done directly. So at this point, what I'd like you to do is just push pause on the video, try these on your own, and then when you resume, I'll discuss their solutions. So for the first one, we see that we just have u squared, so we'll increase the exponent by 1 and get u cubed, and then we take the reciprocal of 3, which is 1/3, and that becomes the new coefficient. And then, as always with indefinite integrals, we add the plus c. Now, with the square root of u, the second one, what we first should do is put it in exponential form. So we have u to the 1/2, and now we can just use that regular power rule kind of antiderivative. So we take 1/2 and we add 1 to it, we get 3/2, and then we'll take the reciprocal of 3/2, which is 2/3, and make that the coefficient, and then we add c to it. Now this third one here, the integral of du over u squared, again, write that as a just a simple exponent, and so it becomes u to the -2. And so when we find the integral of it, we add 1 to -2, which makes it -1. We'll take the reciprocal of -1, which is -1, make that the coefficient, and add c. The fourth one, or before we talk about the fourth one, negative u to the -1 can be written, of course, as -1 over u plus c. Okay, so the last one has the square root of u in the denominator, so we'll just write that as an exponent with a -1/2, and so when we add 1 to it, we get u to the 1/2, take the reciprocal of that, and that becomes 2, the coefficient, and then we add c to it. So those are 4 basic integrals, and we're going to find that we're going to use these a little bit later on in this discussion. Okay, so before we actually get to substitution, we're going to need to talk about differentials, and recall from our earlier classes that a differential is just a derivative put in a form where we have du, and then we have some expression times dx, and that's very similar to having du over dx, but we're going to have the dx on the right-hand side rather than underneath the du. So you can push pause right now and see if you can find the differentials of these. Remember that the dx goes at the end, and see what you get. So go ahead and push pause and try these out. Okay, so with the first one, the derivative of 2x plus 5 is just going to be 2, and then, of course, by the chain rule, since we always use the chain rule on everything in finding derivatives in the differential form, it's going to be 2 dx. The second one, we have x squared, so the derivative of that is going to be 2x dx, and then, of course, the derivative of 1 is 0, so we don't have to write anything for that. And the third one, the polynomial x squared plus 3x minus 7, we take the derivative of that, and that becomes 2x plus 3. And I put that in parentheses before I write the dx, because the dx applies to both the first term, 2x, and it also applies to the 3. So hopefully that all seems quite straightforward at this point. Okay, so we'll get to the main topic of substitution here. And what substitution is all about is that we want to make an integral simpler by using a function to stand in for a more complicated function. And so what we're going to do then is it ultimately will utilize the chain rule of differentiation in a backwards sort of form. So what we're going to do is essentially undo the chain rule, and you'll see what happens with that when I talk about it a little bit more theoretically here. Okay, so there may be more than one way to do all these problems, and in fact most problems in integration you can probably make reasonable arguments to do the integrals in more than one way, and that's all okay. You end up with an integral that's the same value, so there is essentially more than one way. The examples that I'm going to do today, perhaps that doesn't apply to, because they're going to be relatively straightforward and simple, and so I would say most people who know how to do this would do it all in about the same way. Okay, so let's look back at the chain rule. Let's say we have a function f at x, capital F at x, and we take the derivative of that. We'll call it lowercase f at x. Okay, so that's just the basic function and how it relates to a derivative. Okay, so if we were to take the integral then of f at x, we would find the antiderivative of capital F at x, and so these two statements, f at x equals capital F prime at x, is the same thing as saying the integral of lowercase f at x dx that equals uppercase f at x plus c. So that's the same thing. So let's take that capital F at x and let's put in a function g at x on the inside. Now we know how to take this derivative. We apply the chain rule. So what we do is we find the derivative of the outer function, capital F. We leave the inner function alone, and then we multiply it by the derivative of the inner function. Okay, so that's something that you all know how to do. And so we'll then take this, and since capital F prime is lowercase f, we can rewrite this as f at g at x times g prime at x, and that's the derivative of capital F at g at x. Okay, so let me rewrite this in integral form now. I'm going to take this expression here, and I'm going to put it in an integral, and so what we expect is that the result of this integral is going to be this expression right here. So it's going to be capital F at g at x, and then of course we always add the constant of integration c. So here's the main idea. What we're going to do is we're going to find a function u, and that's going to be the function that we use to make the substitution. And then we're going to take du, and that, of course, is going to be g prime at x dx. And you remember from the second set of exercises I have you do, basically just finding the differential form of a derivative is the same thing as finding the derivative, and it ultimately gets multiplied by x. And so what we're going to find is we'll be able to take the derivatives of integrals in this form, where we have some outer function, f, and some inner function. And the key to identifying when you can do these things is that outside of this outer function, we have a g prime at x dx. And this can be in any order. This g prime at x could be in front of this or whatever. And you'll see that in a few examples. So when we see this form, what we do is we can say, well, g at x is u, and so since g prime x at dx equals du, here we can transform this more complicated integral here and make it into a simpler integral here. And then what we do after that is we take our definition of u and apply it back. And so we get essentially this. Okay, let me go back to that. So the whole idea here is that we're going to look for a pattern in our functions, or in the integrand, that's going to have this, where we have an outer function, an inner function, and the derivative of the inner function all in here together. Okay, so theoretically that's probably a little bit confusing, so let's go over a few examples. Okay, so let's say I want to integrate this function 2x times the square root of x squared plus 5. There's no way that we can directly do that. So what we do is we notice, oh, we have an outer function, and that'll be the square root function. Inside that square root, I'll call it the inner function, is x squared plus 5. And now to see if this whole thing will work, we'll find the differential of the inner function. And so that becomes 2x dx, right? That's just the exercise that we had at the very, in the second part, is finding this. And notice that this 2x dx appears here as this 2x dx. And like I said, the order doesn't matter, and very frequently it's split up like this. So what we have is, what did I say here before? Well, we'll just go with it. Okay, so we have u and du. So that inner function is x squared plus 5. The inner function differential is 2x dx, and the outer function is the square root. So we can rewrite this as the integral of the square root of u du. So notice all the parts are here. We got this the square root of u, which is this square root of x squared plus 5. We have du is 2x dx, so that orange becomes this just this one single orange element, and now we have the integral of the square root of u du, and that's something we did at the very beginning, so we know what the answer to that is. That's going to be 2/3 u to the 3/2 power plus c. Okay, so we're not really interested in the outer function or the function definition of u. We're interested in making the substitution back because we're interested in finding the integral with respect to x. And so we substitute back in what our original definition of u was, and we get x squared plus 5 on the inside here. So it's probably a good idea at this point to see that this works out. So what I would suggest you do is push pause here, and then take the derivative of this function that we just found and show that we actually get this function up here. Okay, so the next example, we're going to have this as 1 over the square root of 2x plus 5 dx. Okay, again, there's no direct way to do that because we have kind of a complicated layout of functions here. So let's say I'm going to take my candidate for u as 2x plus 5. So that's going to be that inner function that I'm so interested in. Then the differential of that is du equals 2 dx. We found that from the beginning. And then the outer and then we don't have a 2 here anywhere as a coefficient. So what we're going to do is we're going to take this 2 and we're going to make it part of the du as 1/2 du equals dx. So we divided both sides by 2, and this is what we get. So now we have this piece completely taken care of. We have that inner function 2x plus 5 defined, and now we'll rewrite this with our outer function being 1 over the square root. So that's what we have by substituting all the parts. Okay, so the first thing we'll do is we'll factor out the 1/2 because that's the way coefficients will work. We just don't need them in the way. And we're left with the integral of 1 over the square root of u du. All right, we've already done that. We know what that answer is. So that's going to be 2u to the 1/2 plus c. And then let's get back to x because that's what we're interested in. So we'll take our definition of u and we'll put in 2x plus 1, or 2x plus 5, excuse me, and we get our integral. So notice that these coefficients, I did cancel out the coefficients because I can do that. That 1/2 was not around the 2, so that just cancels out to 1. Okay, so here's one for you to try, and I'm even going to give you the hint that u should be x squared plus 1, and do all the parts now. You want to, or all the steps, you want to find the differential of u, and then you want to adjust coefficients if you need to, and then rewrite the integral in terms of u. And so you can push pause and do this, and then I'll discuss the solution. Okay, so if u equals x squared plus 1, then du equals 2x dx. So I don't have a 2x here, I just have an x. And so what I want to do is then divide both sides by 2, and I get 1/2 du equals x dx. And now everything can be substituted out. Okay, so it's going to be u squared, which is my inner function squared. And then I have the 1/2 du is what's going to be x dx. And so then I'll factor out the 1/2. Now at this point, I want to make a very important check on yourself when you're doing this. What you have to do here is make absolutely sure that when you've made the substitution of u in an integral, that you have no instances of x anymore. You need to define a different u, or you need to check how you made the derivative of that if you end up with x's inside the integral. In other words, you don't have all the things set for doing substitution. You need to do something differently than that. So in this case, I have u squared du. Perfect. Everything's in u. There's no trace of x here. Okay, so I already know what that integral is, and that's going to be 1/2 times 1/3 u cubed, and then our integration constant. So I take the 1/3 times 1/2, and I put in the x squared plus 1 instead of u, and all that's to the cubed. Okay, so here's a couple more for you to try. The first one, use x squared plus 3x minus 7 as the first substitution. The second one, I won't give you a hint, but I think it follows the pattern as much as as the previous example. So we'll go ahead and just simply do that. So push pause and see if you can do these. Okay, so what we have here now, I'm going to just rewrite these because I don't have enough space to do it. So let's take that first one, the integral of 2x plus 3 over x squared plus 3x minus 7. Okay, I'm copying that. And so I'm going to make use of my hint, and I'm going to find du equals 2x plus 3 dx. And then I'm going to rewrite my integral in terms of those definitions. Notice that I have 2x plus 3 dx in the numerator here times dx. So that's why I get 1 times du. And then the denominator, I have my definition of u squared, so I'm just going to do u squared. Find the integral of that, or rewrite it so I have a single exponent, -2. And then we've done that earlier where it's negative u to the -1 plus c. And so I'll rewrite that as -1 over u plus c, and then resubstitute in my definition of u, which was x squared plus 3x minus 7. And of course, feel free to try this. Try taking the derivative of that to show that you actually get the right answer by having the derivative equal to that integrand. Okay, so now the next one. What I'm going to use for u is that what's inside the square root, so that's x cubed plus 1. I'm going to find the differential of that. So the derivative of x cubed is 3x squared, and then it's a differential form, so it's dx. And notice now I have a 3x squared dx. I don't have a 3x squared anywhere here. I just have an x squared dx. So what I'm going to do is I'm going to divide both sides by 3, and so I get 1/3 du equals x squared dx. Okay, now I have the parts to make the substitution. And so what I have then, I'm going to factor out this 1/3, which I can do, and I'm just starting out by writing it on the outside. And then the rest of what I have is just simply the square root of u. You can see that here. And so when I take find the integral of the square root of u du, I get 2/3 u to the 3/2. And so I have two coefficients to multiply by each other. I get 2/9 put back in my definition of x, or my definition of u, which is x cubed plus 1, and write my plus c. And so I'm done. Okay, so how do we do definite integrals with this? There's two ways to do it, and I'm going to insist that you do it one way, this way. It's possible once we find our integral, we move everything back in terms of x, and then we just solve our integral that way. It almost always leads to more computation that's necessary. So the approach that we're going to use on this is that we're going to transform the integration limits to be stated in terms of u. Because remember, if we have integration limits, those are actually in terms of x if we're using x. So for example, if we have this integral, this is the same thing really as writing x equals 0 to x equals 4. And so what we want to do here is we want to take this and change the values of x into the values of u. And the advantage of doing that is that once we find the integral in u, we'll have a simpler integral than if we resubstitute the definition of u in terms of x in there, and we'll just directly evaluate the values of u. Okay, so rather than theoretically, let me do this practically with this problem that I stated. So we're trying to find the integral of the square root of 2x plus 1 dx. And so u is my inner function is 2x plus 1. The derivative of that is 2 dx. And then we have, we don't have a 2 anywhere in the integral, so I'm going to say that's 1/2 du dx. Now what I'm going to do is I'm going to transform my 0 and 4 in terms of u. So with my definition here of u squared, or u equals 2x plus 1, I'm going to say when x equals 0, that must mean u equals 1, right? I just plugged in a 0. 2 times 0 plus 1 gives me 1. And so the upper limit is when x equals 4, I know u equals 9. Okay, so what this allows us to do now is restate the integral not only with the new variable u, we'll have new integration limits. And so this 0 to 4 times the square root of 2x plus 1 as an integral transforms into 1/2. Remember, that's what we get from our differential element here. And then we just have a du and then the square root of u, and we know that our integration limits are 1 to 9 because when x was those values, u is now 1 to 9. And so calculating the antiderivative here is of the square root of u is just going to be 2/3 u to the 3/2, and then I'll just plug those values in. So I'm going to keep this, the coefficient of 1/2 times 2/3, multiply that, keep it as 1/3, put it in parentheses, and then substituting in here I get 9 to the 3/2 minus 1 to the 3/2, and that was my integration limits. Now 9 to the 3/2, don't reach for your calculator. Recognize that when you have a fractional exponent, the denominator is a root. So 9 to the 1/2, of course, is 3. So we don't have to use a calculator there. We know the square root of 9 is 3, and then 3 cubed is 27. So I get 27, and then 1 to any exponent is just 1. And so when I evaluate that, I get 26 thirds. So I kept the whole thing in terms of u from the outset. And that's really the way to do these. We don't go back to x, we just stay entirely in u. And calculating these at the beginning, may seem like an extra step, but it's really a process saving step by not having to go back to x in these things and have a more complicated function that we're calculating two different values from. Okay, so here's one for you to try. We'll see if we can do this integral. Find a candidate for the inner function, find the differential element, and then transform the values of x equals 1 to 2, make them in terms of u. So push pause and try this. Okay, So what we get, a good candidate for u is 3 minus 5x. And so du equals negative 5x. That's just the derivative of negative 3 minus 5x. And then we don't have a negative 5 in that original integral, so we'll divide by negative 5 and we'll get negative 1/5 du equals dx. Okay, so then from here, we're going to transform the values of x. So when x equals 1, we plug in a 1 here. 3 minus 5 times 1 is going to be negative 2. So when x equals 1, u equals negative 2. And then the upper limit is going to be 2. So when x equals 2, we put a 2 in here, and we get 3 minus 5 times 2, which is negative 7. So we have everything to rewrite our integral with. And so a couple things going on here. We'll first factor out the negative 1/5, and then we're left with the integral of 1 over u squared. And so we know that that's going to be negative 1 over u. Now look at all these negative signs. So I have a negative out front of the coefficient. I have a negative in the antiderivative that I found, and then I have negatives in the integration limits. So if you aren't real careful, chances are you might mess up a sign somewhere along the way. I know I frequently do if I don't do this. What I'm going to recommend is that you write plenty of parentheses. So here I wrote parentheses around my antiderivative, substituted in my negative 7, didn't try to cancel anything out. I wrote it all down, minus negative 1 over negative 2. That's putting in a negative 2 in this expression and bringing it down here. And everything is in parentheses. And now that I have the parentheses, it's easy to see where my negatives cancel out. So negative 1 over negative 7 minus negative 1 over minus 2, that gives us this business here. And we still have this negative out front. And so when we make a common denominator, that's 14, 1/7 transforms into 2/14, and 1/2 transforms into 7/14. And so we end up with 1/14, because 2 minus 7 is negative 5, and we have times negative 1/5 make it positive, and so we're at the value 1 over 14. Now earlier when I was talking about the properties of integrals, I was suggesting that you might want to do estimates of what this integral is without doing any computations, just to make sure that you get the right answer. And so here's a great example of this. 1 to 2, this is never negative. And 1 over 3 minus 5x, this value in here may be negative, but this squared always makes it positive. So the value of the integrand, what's inside here, is always positive with positive limits. So we're going to expect a positive area. And lo and behold, that's what we get. We get a negative, or we don't get a negative, we get 1/14. And if I made a mistake anywhere along the line here in treating negative values, it's likely I would have ended up with a negative value here. So just as a real quick and dirty check, you can already see that this integral is positive. So you're going to expect a positive number. And so that's one way to look at it. It doesn't tell you that you're right, but it tells you that on that basis you're not wrong. Okay, so overall some tips. Write out everything neatly and completely. I can't emphasize this more in any kind of math, but don't omit the parts of an integral. So you always write the integration sign, write the function, and always write the dx. Don't ever skip writing the dx. Remember when we were doing Riemann's sums, that's actually the width of the interval. So it's the thing that gives the units square units if you're calculating areas. Okay, and then also, once you find the antiderivative, if it's an indefinite integral, always write your c, and don't write the integral sign or the differential element when we're finding the antiderivative. So keep your notation really nice and tight. Always write equal signs where things are equal. If you're going to start on something else, then you don't need to write the equal sign, but you do need to make it a complete statement. So, I've kind of said this before in other contexts, but with integration, it's especially important that you always write everything down completely. Okay, so use the coefficients to make that du dx substitution exact. So sometimes we end up with du equals something like 2x dx, and if we don't have a 2 in there, make it 1/2 du equals x dx. And what I said earlier is don't ever mix variables. If you end up with an integral that has both x and u in it, you're wrong. You need to go back and you need to either make a different substitution or check how you made the substitution to make sure everything is right. Okay, so that ends the introduction to substitution.